Hello, and welcome to this GGB webinar. My name is Matthew, and I will be your IEEE Global Spec moderator, and I want to review a few housekeeping items with you before we begin. Please take a moment to familiarize yourself with the operation of the user interface for today's webinar. The large window with the heading Presentation in the upper left is the primary window. Just to the right of the main presentation window is the Speaker Bio window with background information on today's presenters. Just below that is the Q&A window, and any time during the presentation, you can enter a question into the box in the lower section of the window and click Submit. Your question will be placed in the queue to address when we get to the Q&A session. At the bottom of your screen, you will see additional buttons to enhance your webinar experience. To see what a particular button does, just place your mouse pointer over it and a tooltip will appear with a description of the button's function. Now I would like to introduce today's presenters. Michael Kim, PhD, Principal Engineer for Tribological Materials, and Marco Enger, PhD, Senior Tribologist at GGB. Michael Kim holds a PhD in Materials Engineering from Drexel University and has spent 25 years in the development, testing, and application of tribological materials. Marco Enger holds a PhD in Mechanical Engineering with more than 10 years of experience in tribology, tribometry, and all related subtopics. In 2014, he became the Senior Tribologist at GGB and is responsible for all fundamental research works related to tribology. Before he joined GGB, he was working for the Competence Center of Tribology at Mannheim University. Guys, welcome to today's event. And with that, I will pass things along to you to get started.
Matt, thanks a lot. This is Mike Kim. Thank you for the introduction, Matt, and thank you for organizing this. And so what we're going to do today, as the title says here, we're going to talk about how to improve fretting wear resistance with self-lubricating surfaces. And if you look at all the three pictures that are in the top half of this slide, every single one of these shows damage that occurred by this type of a wear issue. And every single one of these is going to show up in our presentation today. So one quick one on who's GGB. Well, we make sliding interfaces. A lot of those will show up as bearings that can be seen in one of the top pictures. We also make flat surfaces with coatings or strained surfaces. We make metal polymer bearings that have a metal backing with a polymer lining. We make engineered plastics. We produce fiber reinforced composites. We have a number of metals and bimetals, and we do polymer coatings. And all of those are really designed all to deliver a sliding interface. And we're going to talk about that today in one of these very deleterious methods of wear and damage. Quick word about what this is part of. We have something we call Tribology University, or short TriboU. And basically our TriboU is intended to provide working engineers who may or may not be users of our products, understanding of basic tribological concepts for their implementation in the design, the manufacture, or the use of industrial equipment. And we put this out there because since we are a vendor of tribological materials, we just believe that increasing knowledge in general in this subject matter will help us as a business. And this presentation here is just a part of that. So how are we going to do it today? Well, first we're going to talk about tribocorrosion, which is a combination of wear and corrosion together. We're going to talk about that in a general sense, and then I'm going to yield to Marco, and he's going to come in and he's going to talk about fretting or high frequency, low amplitude wear in a general sense. Then Marco is going to introduce us to the concept of transfer films, which are very important in how many of our sliding products will operate. And then he's going to talk a little bit about the coatings that we produce and a study that was performed in his lab in Germany in the fretting wear of one of these coatings. Then we're going to come back in, and I'm going to come back in, and we're going to talk about composite bearings, and we're going to talk about counterbody effects and their relationship to fretting wear. And then we're going to talk about an advanced composite material that was designed specifically for improve performance in this kind of a wear mode. So, talk about the first two topics. Well, we've used the word tribology a lot already in this presentation, and for those who don't know, tribology is the science of wear, friction, and lubrication, and it talks about interacting surfaces and other tribological elements, how they behave in motion, relative motion to each other. Well, wear, we probably all have an idea of what wear is, but we define it as damage to a solid surface, usually involving material loss, which probably makes a lot of sense to everybody that's listening. And it's caused by relative motion between the surface we're talking about and a contacting surface or substance. Friction, again, we probably all have an idea of what friction is. We define that as a tangential force resisting the relative motion between two bodies that are in contact. And tribal corrosion, which comes right into what we're talking about today, well, that's a material degradation process, which is caused by the combined effects of corrosion and wear, which often is what happens when you have fretting wear and fretting corrosion. So now we're going to talk about film formation on a metal. And sometimes metals will form a passive film, which stays adhered, or sometimes films will form that will fall off and expose fresh metal. So what we've got here, we've got a slide which is we're going to come back in with the same slide later in the presentation. But we bring it in here because we just want to talk about different kinds of films that form, different kind of oxides. And this picture on the right shows a salt fog chamber which sits in our Annecy, France Technical Center. And what it does is we have this thing that's at an elevated temperature. We put a constant salt fog into the air of this, and this nozzle, we have a nozzle which creates a saline fog. And we'll put samples in there, like the ones on the left, for varied times. And so what we have here on the left is chrome plated. This was specifically thin, dense chrome, which is kind of a specialty chrome plate. We've got electroless nickel. We've got 304 stainless steel, which is an 18H stainless. We've got 420 stainless, which is a hardened stainless. And then we've got plain 1040 steel and then case hardened steel. And you can see through this series that there are different kinds of surfaces on these. And the 304 stainless steel shows the most obvious example of a coating that is well adhered and protective. There was one very small spot of rust which showed up after 1,000 hours. You can just see it about the middle of that sample up towards the top. The electroless nickel broke through at about 480 hours. The chrome showed up with rust at 144, but all the others were stopped at 24 hours. Now, we know how rust works. We know it from our cars or things we have in our yard that are exposed to the environment, that rust, like on the two things on the right, will just spall off. They're poorly adhered, and they will expose fresh metal underneath. So this kind of non-adhesion of the surface plays a strong role in how fretting wear and fretting corrosion occur, and we're going to talk about those further. So passive films, when you have a passive film like that stainless steel, well, you can have an active phase in it where the corrosion and the oxidation response prior to the formation of a protective film acts like a material that is unprotected. And then after a short time, it forms a passive film, that is a stable, adherent, protective oxide film that reduces the corrosion rate by orders of magnitude, sometimes up to 10,000 times below that in the active state. And you can have a transpassive state for a film, surface film. And that is when the corrosive environment is sufficiently aggressive to remove that passive film, and then it acts just like it wasn't protected at all. And one of the things that can occur in fretting wear, as we're going to see some very specific examples, is that this passive film can be broken by wear as well as by a corrosive environment. And when it gets broken in a wear environment, sometimes the oxidation occurs faster than the film can reform. And that becomes a real problem when we're talking about fretting wear. We're going to see specific examples of that. Now we've got one specific, I think, very interesting example of tribocorrosion, just to illustrate the idea. And this is Franklin Roosevelt. This is from the Franklin Roosevelt Memorial in Washington, D.C. And this memorial was built in the 1990s, and since the 1990s, Franklin has developed a protective patina. That is this green oxide surface that is well adhered to the metal. And it protects the underlying bronze statue from further corrosion. Now, the problem that occurred in this case, as we see in this red circle, is its visitors to the memorial walked up to the statue and wanted to shake the president's hand. And so they grabbed his finger and rubbed it. And what happened was the fluids in the skin that people are rubbing with are slightly corrosive. They got a very slightly acidic pH. And so this acidic pH combined with the sliding motion of the skin on the bronze wore away that protective patina. So this patina is now formed, it's removed, it's reformed continuously in the cycle of oxidation, tribocorrosion, and reoxidation. And so what will happen if the Park Service doesn't do something about this, that at some point his whole finger will be missing because this underlying bronze is continued to be exposed to the environment. So that's a good illustration of tribocorrosion. So now what we're going to do is I'm going to yield to Marco, and Marco's going to come in and he's going to talk about fretting in a more general sense. Marco?
Yes, so on this slide I would like to give you a short overview about fretting wear. I will not share too many details, but I think you need some basic information to better follow the content of today's presentation. So fretting wear normally occurs when the relative movement amplitude is small. However, what does small mean? A maximum amplitude length of 200 to 300 micrometers is often mentioned across diverse literature sources, but as you see, the information is a bit foggy and not consistent. Further, we also see that this is often not in line with observations in real applications. That said, I would like to provide a more general definition of fretting wear. So fretting wear is defined as, wear is defined as fretting wear when the movement amplitude is smaller as the characteristic contact length of the contact area. This results in a permanent overlapping of surfaces. And the example on the right side shows you this relationship. In this example, the characteristic length is 3 millimeters. When the relative motion amplitude is smaller than 3 millimeters, the contact is prone to fretting wear. So the next question we need to answer is, what are the wear mechanisms of fretting wear? So fretting wear is often an accumulation of all 4 main wear mechanisms. So this encompasses adhesion, abrasion, fatigue, and tribochemical reactions. Another problem with fretting wear is that wear debris often retains or stays longer in the contact zone. This can lead to an accelerated or escalating wear development, especially in the combination with hard oxide particles. The extent of fretting wear can be massive, which can lead to a premature failure of an application. Another motion type that is prone to fretting is high-frequency, low-amplitude motions. So on the next slide, I would like to give you a short overview of potential solutions to reduce fretting wear. So external lubricants can reduce fretting wear. So oils and greases are the most frequently used lubricants for reducing fretting wear. However, they are only effective until the lubricant is displaced from the load zone. This situation is very common and is one of the main reasons why conventional lubricants can fail in such conditions. Solid lubricants like PDFE, graphite, or molybdenum disulfide are also very effective in reducing fretting wear, especially when they are used as a bonded structure, like a composite or an anti-friction coating. When they are used in such a structure, it is very hard to displace them from the load zone. In situ oxide formation is also a well-known side effect for fretting contacts. These oxides can be either lubricious, abrasive, or both, but in many cases, oxide formation has a negative impact on wear. The formation of a transfer film, especially when using solid lubricants, help to effectively reduce or to prevent threading wear. And to do so, the film must be consistent and really robust. So throughout the next slide, I would like to talk more about transfer films. So materials with an intrinsic solid lubricant lubrication provides the feature to form transfer films on the attacking counterface when stressed tribologically. So the inevitable wear of these materials when sliding against the harder counterface generates wear debris. This debris can exit from the contact or may stay and preferably deposit to the counter surface. So when debris sticks, it can form a transfer film which potentially protects the contact from further wear damage. A high protection rate can be achieved when the film has a high quality. High quality is often accompanied with some essential properties. So the film formation needs to be consistent or uniform. This means that the transfer film has a good masking quality. The other essential property is it needs to be robust. So when the film is robust enough to withstand the ongoing tribological stress action, it can protect the contact from further damage. Transfer films are very thin structures as shown on the fifth section on the right side of that slide. Their thickness is normally below 1 micrometer. To get a feeling about how thin that is, we can compare this to something we really know, which is the human hair. When we compare both thicknesses, we see that the transfer film is roughly 100 times thinner compared to the human hair. The image on the right side shows us this thickness relation. So the big circle is the diameter of a human hair, and the small dot equals the thickness of a transfer film. It is believed that the quality of the transfer film is affected by diverse factors dictated by the related tribological system. As a reflection, it can be postulated that the transfer film could also be understood as a response of a specific tribological system, encompassing following aspects: the induced collective stress, the specific property profile of the opposing surface, the composition of the self-lubricating material, and most likely the conditions of the surrounding atmosphere are factors to consider. So one of the biggest challenges is to design materials that form high-quality transfer films even under very demanding application conditions. This slide shows you the impact of transfer film formation on the performance of a dry running sliding contact. The results on this slide were generated using a simple pin-on-disc model test setup. The material pairing tested was a polymer composite which slid against the steel counter surface. The steel counter surface had a surface finish of roundabout RZ 1.5 micrometer. The system starts with a high running in wear rate during the first few sliding meters. With progress in covered distance, the wear rate declines until the system enters the operational performance window. You see that breaking in point at approximately 400 meters. This reduction in wear is explainable through diverse running-in effects occurring within the contact interface, including the formation of a protective transfer film, and we clearly see that transfer film on the SEM image on the bottom of this slide. So the dark areas are the organic polymeric film, and the light areas in this image are the initial steel counter surface. Despite that the transfer film incoherently masks the counterface, it reduces the abrasive accuracy of the counterface and thus leading to an improved wear performance of the contact. This slide summarizes the main facts about transfer films. So these films are essential for a satisfactory functioning of dry running tribological contacts when using self-lubricating materials. Composite material used in such contacts are specifically designed to form robust films with a high masking quality, even under the most severe operating conditions. Such films are very effective in reducing wear under threading or high-frequency, low-amplitude motion conditions. The image on the right side shows you a macro view of a well-developed transfer film on a metal shaft. The film was generated by a PTFE lead-based composite bearing material. So throughout the next slide, we want to show you different material concepts with excellent intrinsic solid lubricant lubrication. Further, we will show you that these materials can effectively reduce damages by threading wear or high-frequency, low-amplitude motions. I will start with polymeric coatings. On this slide, I would like to share more information about coatings. This schematic illustration shows you an exemplary architecture of a polymer-based coating material. So a polymer coating consists of a matrix polymer. The expression binder material is also frequently used as a substitute for matrix polymer. Technical polymers are normally used as matrix material to ensure the full performance of today's polymers. And we can find the whole spectrum of the polymer triangle or pyramid. These materials are modified using solid lubricants as light active elements, and we can also add other functional fillers, for example, to improve the wear resistance of such coatings. Typical solid lubricants are PTFE, graphite, hexagonal boron nitride, or MOS2. These coatings are normally directly applied on the surface of the moving components using the typical application methods like spray coating, dip spin coating, just to name a few. After the application and the two-step curing process, the coating adheres well to the substrate. After the curing process, the standard thickness is in the range of 25 micrometer. The coating illustration shows you that the functional fillers are homogeneously distributed within the polymer matrix. The slight active fillers are stratified. This has two advantages. So a stratified filler do not harm the adhesion between coating and substrate. Further, this filler gradient also provides the advantage of a high filler concentration close to the load zone, leading to low and constant friction. As already stated, threading wear can be very severe for applications and thus leading to a potential pre-major failure. A test matrix was conducted in collaboration with the Competence Center Tribology at Mannheim to show the benefit of using self-lubricating coatings. The test matrix encompassed different material pairings. The reference pairing was a typical steel-steel pairing that is frequently used in such conditions. Different steel coating pairings were also investigated. The testing setup is shown on this slide. A flat-on-flat contact geometry was used. The area contact was controlled using a contact pressure foil. The contact was loaded with 1 kilonewton corresponding to a contact stress of 50.6 megapascal. The motion type was linear reciprocation at a frequency of about 50 hertz. The movement amplitude was set to 200 micrometers, and the tests were performed at different temperature levels. For pre-screening, the test duration was around about 4 hours. The long-term test was stopped after an obvious failure of the contact. Throughout testing, the tangential and normal force were recorded, as well as the temperatures and the sliding stroke. The test was frequently interrupted, and the contact was opened for a very short time to automatically take images of the contact. This image series helps to document the wear progress throughout testing. This slide shows you an exemplary test readout of this testing. So the first diagram illustrates the tangential force and the normal force, as well as the stroke during testing. The second diagram shows you the temperature recordings. As already stated, throughout testing, images were taken from the contact to document the wear progress. The results of the steel-steel reference pairing are given on that slide. The test duration was 4 hours. After 4 minutes, we can already identify the first adhesive spots. Threading corrosion already started within the first 60 minutes. The border area of the contact indicates a massive formation of oxide particles. With progress in sliding cycles, we see that we have an escalating wear development, so that the formation of oxide particles is really immense. The images also indicate that wear particles can stay longer in the contact. All images show oxide particles across the entire contact zone. This can really add to wear, because oxide particles can be really aggressive in terms of abrasive induced wear. Overall, the performance of this contact can be classified as insufficient. So this image shows you the performance of a steel coating contact. The image after 5 minutes shows no damage of the coating, so the coating is still intact. After 60 minutes, the coating starts to flake off. The delaminated coating part is clearly visible on the lower left border of the contact. Such a delamination is often a result of a weak adhesion between coating and substrate. The coating wear progresses, leading to an exposure of the underlying steel substrate. In those areas, clear threading corrosion can be identified. So we have a massive oxide particle formation appears when the coating failed completely. So this contact can also be classified as an insufficient performing contact. So this image series represents a good performing coating steel contact. Looking at the images, we see only minor running in wear marks on the coating surface throughout the whole throughout the entire test duration. This result shows impressively that the advantage of using polymer-based coatings for threading-prone contacts. This is a summary slide of 3 well-performing coating systems. 2 coating systems were tested from the PEC family, and 1 coating was based on polyamide imide. The images shows both surfaces, the coated sample and the counterbody. What we can identify is that we have only a negligible running in wear on the coating surface. We just see that it's a running in wear. The counter surface inspection also indicates the onset formation of a transfer film, and the darker areas on the counter surface, this is the transfer film. So overall, we can say that this is that these are very well performing surfaces, contacts. Sorry. So far, the results are promising. However, a long-term test was performed to see the long-term stability of polymer coatings under threading operating conditions. To make the test even more severe, the temperature was altered between room temperature and 120 degrees. As already stated, the contact pressure was 50.6 MPa. The movement amplitude was set to 200 micrometers in combination with an oscillation frequency of approximately 50 Hertz. The results are shown on that slide for this long-term testing. Previous observations showed that a steel contact is very prone to threading wear. The results also revealed that a steel contact can fail early. Under such conditions, the contact already failed within the first 4 hours. The long-term test for the coating steel pairing showed us that this contact survived over 70 hours in such demanding conditions. So again, that is a good result to see the benefit of using polymer-based coatings. This is my last slide. So the image series shows the wear progress of the coating throughout the 72-hour long-term test. During the first 50 hours, the coating is still intact. The surface image only shows minor wear marks, which is running in. After reaching 72 hours, the coating starts to wear significantly. This coating wear explains the increase in the tangential force shown on the previous slide. We have seen that. Yeah, so you see that. So that is the tangential force. So here we have a really stable friction response. But at this point, we see a clear change in friction, and that is because the coating starts to fail. So I think previous slides showed impressively the advantage of using polymer coatings for fretting-prone contact. So I will hand over to my colleague, Mike Kim, and I would like to thank you for your attention.
Thanks a lot, Marco. We're going to continue to talk about different materials in similar modes of wear. And we're going to talk about first composite bearings and the counterbody effects in using composite bearings. Right here, this is what we're talking about. One of the bearings that we have used and sold for decades. This is you can see the bearing in the middle there. On the left is a cross section of it, and it's basically it's the same area but shown in two different colors to show two different features. And you've got in the bottom part of the picture, you show that's got a high-strength fiberglass backing, and the tribological part of this bearing shows that it's made up of a combination of polyester fibers and PTFE fibers. It's all held together with an epoxy resin with some graphite fillers thrown in there. And on the right side is a schematic of how we test this bearing normally. And in this case, we're testing this with a 1-inch or 25.4 millimeter shaft, 13.3 millimeter amplitude, which is plus or minus 30 degrees and 15 cycles a minute. And in this case, the case I'm going to show you in the next slide was done at 70 megapascals or 10,000 psi. So this graph on the top shows a plot of the friction through sliding distance in kilometers, and the 2.5 kilometers in sliding distance is equal to approximately 100,000 cycles. And you can see that the friction started at approximately 0.1 friction coefficient. It quickly dropped after just a few cycles down below 0.075, and it stabilized and stayed for the duration at approximately 0.04, which is a very good, low, stable friction for a self-lubricating bearing. And the image in the middle, on the bottom, shows the shaft after testing, and you can see this transfer film which has been forming throughout the process. And this is a picture after 100,000 cycles. So it is the formation of this transfer film which started early on in the process, which allowed the reduction and stabilization of the friction force and the wear as a result. So when you're down around 0.04 friction, the wear of this bearing is going to be very low. So remember, that was in large angle oscillation. And so now we're going to run a study in small angle oscillation. And so what we did is we took the same bearing, it's the same picture, and we ran it against a series of different shafts. Now you will remember that image we showed early on with the series of shafts that were corrosion tested. Well, that was part of this study. And so we tested against 304 stainless, we tested against 420, against plain carbon steel, against case hardened steel, against an electroless nickel coating, and against a chromium coating, a thin dense chrome coating. And again, this picture that you're seeing was a salt fog tester that we used. And on the right is a wear tester, which is similar to the one we talked about a few slides ago, but the difference here is that the load is lower at 30 megapascals compared to 70 in the previous, and we've got a plus and minus 1 millimeter or plus and minus 5 degree oscillation, and we did this at 200 cycles a minute. Now I want to concentrate on a statement that Marco made when he was talking about fretting in general. And he said that oftentimes people talk about amplitudes of 300 microns or less. Actually, when academic folks are talking about fretting, actually 300 is high. So if you go out to tribology conferences like Marco and I do, and you listen to people talk about fretting, you basically run into two totally different kinds of people. You got to talk about the academic research who talks about amplitudes of 100 to 150, and then you hear industrial guys like Marco and myself talking about amplitudes of, here in this case, plus and minus 1 millimeter, because we still see similar performance. We still see the same kinds of results, but these kinds of amplitudes are much more applicable to the type of conditions that our customers are going to see in their equipment. So let's keep that in mind as we go through this. Again, these are the same. This is, again, same picture we showed before. Now, what we have here on the left is what we do is we measure the time to red rust formation as a measure of the corrosion resistance. And they looked at it in the lab in that salt fog tester. The first time they looked at these was 24 hours. So the ones on the right are pretty well corroded, especially the 2 on the right are very well corroded at 24 hours, and they probably had red rust showing up in maybe even in minutes. But as you can see, the durations here plotted are the 420 hardened stainless was at 24 hours. The 1040 plain carbon, 24 hours, and the case hardened steel was 24 hours or less. Thin dense chrome was 144. Electroless nickel was up around 480, and the 304 was just barely showing anything at 1,000 hours. And in a follow-up study, I'll just tell you that 316 stainless showed nothing at 1,000 hours. So now what I'm going to do is I'm going to show you some wear results. And then what I'm going to do is I'm going to show you some images of the failed parts. And then I'm going to bring back in this exact same slide we're looking at right now, because I think it'll be easier to understand. So what happened was we measured in 2 ways. We measured the wear of the different shafts after testing, after oscillating, like we said, and we measured that as an increase in roughness. And you can see that here's the as-received roughness. The chrome, the nickel, and the 304 stainless had very little. In fact, this roughness increase was only the transfer film. There was no damage to the metal, as we're going to see. But the 420, the 1040, and the 8620, which was case hardened, had significant increases in roughness. And as we look at the bearing wear, what we see is that there was very little bearing wear for these 3, the chrome, the nickel, and the 304. And then the 420, the 1040, and the case hardened all had increasing amounts of wear in the polymer bearing. So the left is looking at the shaft, the right is looking at the polymer composite bearing. And what you can see is that the wear of the bearing followed directly with the increase in roughness of the shaft, which leads to the conclusion that the roughness of the shaft, the increase in roughness, caused the wear on the bearing. Now let's look at some images. Okay, here's the 420. Here's the bearing on top, which was cut in 2 so we could see it. On the top right is just a close-up of the same area that's in the red box on the left, on the shaft. So the red boxes on the left show that those 2 areas matched up with each other during the test. And in fact, that the area, so what happened was, in this area, you can see it's a rough surface, and oxidation occurred, and this oxide was transferred to the surface of the polymer bearing. Now, as we analyzed that, I don't know if you can see this too well, but that area showed a lot of iron and chromium in the bearing, on the bearing. So this analysis on the bottom right was taken from the bearing, and since we know that there were iron and chrome in the shaft, we know for certain that the shaft material oxidized and transferred to the bearing. Here's the 8620, the case hardened. What you can see in the top left, that's the bearing that was disassembled. The shaft was taken out of it, and that residue that's right in front of the bearing is rust or oxide. And the middle image shows the surface of the shaft, with a heck of a lot of rust on there. And then the top right shows scoring on that shaft. And then we did an analysis of the residue from the bearing, and sure enough, it's iron, meaning it came from the shaft. So again, the shaft oxidized. That oxide spalled off. It became wear debris in the system, and then it continued to oxidize again. And if you will remember from the data that the 8620 case hardened had the highest amount of roughness and the highest amount of bearing wear. Electroless nickel, on the other hand, showed a very stable transfer film. Look at the top right. That shaft showed a very stable transfer film. The middle is just a highly magnified image of the same transfer film, as is the one on the left. So you remember that electroless nickel had no roughening and very little bearing wear. And if you look at the analysis on the bottom, you can see some fluorine in that transfer film. Remember, there was PTFE in the bearing, and just a very, very small amount of nickel showed up. So in other words, that PTFE in the bearing, some way or another, transferred to the nickel shaft, protected the shaft, and protected the bearing. Again, I said we'd come back to it, and we will. Remember, we said the graph on the left showed the roughening, showed the roughness after testing. The case hardened was the highest, 1040 below that, 420 again, and then the other three had very little. And again, the roughness of the bearing, the roughness of the shaft led to wearing of the bearing, as you can see on the right. So this really showed that the best transfer film formation led to the least damage of the shaft, which led to the best performance of the bearing. Again, to see it laid out, we tested these 6 shaft materials, 304, 420, plain carbon, case hardened, nickel, and chrome. All the steel shafts had some oxidative wear. Even the 304 had a little bit. But the greater the corrosion resistance, the greater was the resistance to oxidative wear. Shaft hardness had no effect on shaft wear because the hardest of all was that case hardened 8620, and it had the most roughening, it had the most wear, and it caused the most bearing wear. And the non-ferrous coatings had no oxidative wear at all. So these were adherent oxide films that were on the nickel and on the chrome, and these adherent oxide films didn't go anywhere. They stayed right where they were, and they were protective of the shaft. And stable transfer film formation accompanied the reduction or elimination of oxide wear. And in the red box down at the bottom left, it says that the control of oxidative wear in the dithering condition improved shaft corrosion resistance and was helped by improved shaft corrosion resistance and helped by stable transfer film formation. So now let's talk about a composite bearing designed specifically for fretting wear resistance. The one we talked about a minute ago, this last study, has for decades been doing a great job in the market for large angle oscillation. But as you can see, under certain conditions, it's not so great in fretting wear. So let's talk about when you design for that. Here we have a wicket gate. This is a piece of a hydropower turbine. And what we have here, you can see this blue arrow where the water is coming into the turbine. That's going through the wicket gate. And so the wicket gate controls the flow into the turbine. And what's happened to these wicket gates is they're sitting there stationary all day long, being buffeted by this huge water flow. So they're vibrating back and forth in a very low angle oscillation. And then every once in a while, the operator of the turbine will want to change the water flow. So they'll try and get these valves to move in one large angle oscillating motion. And so there is an industry standard test, and we're going to start to explain it on this slide and explain it further on the next, to simulate performance of bearings in a wicket gate. And that test was developed by the U.S. Army Corps of Engineers. You can see the specification. And so what it is, it's a dithering condition. It's a combined set of conditions. One is a dithering condition at 23 to 30 megapascals oscillating load, plus or minus 1 degree, and 2 hertz. It's got a 125 millimeter, about a 5-inch shaft. And then they'll run that for a while. And then every once in a while, they'll do a large angle, it's 15 minutes. and it's plus and minus 15 degrees and a very 10-second full sweep. So it simulates the whole operation of this wicket gate. And it uses a hardened stainless 17.4 pH stainless shaft. It's 50 Rockwell C, and typically a roughness of 4.4 micron RA or 16 microinch. So we at GGB, we simulated this test. So we simulated the simulation. And what was important to us was that our simulation had the same amplitude, which is plus and minus 1 millimeter, which here I'm going to highlight what I said and what Marco said previously, was that this academic definition of fretting wear doesn't really work well in our customer base. And so this was plus and minus 1 millimeter. We ran it a little faster and a little higher load, 30 MPa constant and 3.3 hertz. So what happened? So we're going to compare two different bearings. We're going to compare the one we already talked about, that composite bearing from the previous study. That one's on the left, and we're going to call that baseline composite. And then we have an enhanced dithering composite, which is designed specifically for this kind of condition. And it also has polyester and PTFE fibers. It also is held together with this epoxy. It also has a high-strength fiberglass backing, but it has a different filler package, which was designed to form a stable transfer film over a broader range of conditions. Those conditions included both of the conditions in that wicket gate. So this bearing was essentially designed to perform well in that U.S. Army Corps of Engineers test. So this is similar to before. The shaft on the left shows, the graph on the left shows the shaft roughness after wear testing. The shaft on the right shows the bearing wear. And again, we've got our baseline composite, which we talked about before, and this enhanced dithering composite. Let's talk about the shaft roughening first. Well, 1040 steel. You can see I had actually the 1040 data is the same as before from that same test. The 420 stainless, you can see, was from before. If you remember, I'm going to show you again, but the image of the 420 had areas of transfer and areas of roughness. So what we did is we plotted both of those here. The chrome, the chrome had, with the blue diamond, had some increase in roughness, but that was all from the transfer film formation, not from the roughening of the shaft. But when we look at this enhanced dithering composite, again, looking at the shaft roughness, there is no increase in roughness whatsoever. It formed a stable transfer film all the way along all these different shafts. And so if we look at the graph on the right, which is the bearing wear, again, the 1040 had a lot of wear. 420 had some, but in the thin dense chrome coating, the bearing had very little. But in the case of the enhanced dithering bearing, low wear all the way across the board. 1040, 420, and the chrome coating. Why was that? How did that occur? Well, I'm just going to show you the 420 because it's such a dramatic difference. Well, the left is run with that baseline composite that was designed for large angle oscillation. The right is 420 tested with this enhanced dithering composite. You can look at the transfer film difference. It's uniform on the right, uniform, stable, even all the way across the load zone. The one on the left with the baseline composite, it has that rough area. The roughness went all the way up to 1.5, whereas it stayed stable at 0.35 with the enhanced dithering composite. The one was designed to form the stable transfer film. Let's look at the residue that was removed and analyzed. Well, the one on the top shows the residue from the bearing tested with the baseline composite. A lot of iron there. You remember the image with that rusty spot that had transferred over to the bearing. And then one on the bottom, nothing. Had some fluorine there, transferred from the PTFE. Other than that, nothing. Stable transfer film, beautiful performance. Again, same data we saw before. The baseline composite had a lot of roughening with the shaft. Enhanced dithering had no roughening and very little wear. So this baseline composite, as it says down here at the bottom, was highly dependent on the shaft composition and the shaft roughness from the oxidative wear increased the bearing wear. But this enhanced dithering composite, we had low shaft and bearing wear, no shaft damage whatsoever, as a matter of fact. So it just shows the effect of stable transfer film formation on performance in this kind of a wear mode. So that's going to bring us to the end, and I think we're going to have some time for questions. So our summary was we discussed tribal corrosion, we discussed adherent and non-adherent oxides, we discussed fretting, we discussed high-frequency, low-amplitude wear mechanisms. We discussed transfer films and their role on reducing fretting and HFLA wear. We discussed polymer coatings, and Marco showed data how good performing coatings improved wear and fretting. Then we discussed composite self-lube bearings, the effects of counterface composition in this kind of a wear mode that we're talking about. And we showed the effects of bearing composition for improved transfer film formation. And that brought us to the end. So now we got roughly 10 minutes left. I think we can actually go over that a little bit if we have questions to answer. But at that, we'll open it to the floor.
All right. Thanks, Mike, and thanks, Marco, for that great presentation. And thank you for all the attendees for being a part of today's webinar and your submitted questions. If you haven't already submitted your question, you can do so now by entering it in the Q&A box and clicking submit, and we'll try to get to it in the time left. Okay, our first question is, do you need to roughen the substrate surface before you apply the PTFE composite coating?
I will answer that, Marco speaking. Yes, we normally pre-treat the metal substrate using a grit plastic process. So we make it rougher. This helps us to improve the adhesion through a mechanical anchoring effect between coating and the substrate. So yes, that is a normal process.
Great, thank you. Okay, next question. Is 70 MPa demanding condition for PTFE applications? Excuse me, is 70 MPa a demanding condition for PTFE applications?
Yeah, 70 megapascals. I'll take that one. We make a broad range of bearings types and surfaces, and some of them are coated with a PTFE-based coating, if you would, multi-layers with steel, bronze in the middle, and PTFE on as a coating. For that, 70 MPAs would be quite dramatic. For this composite that we're talking about here, it runs typically at much higher loads. And 70 MPA is actually not that tough. It'll actually perform well at 140. So it really depends on the bearing type. And so we have a broad range. We have dozens, if not more, different materials, all of which are designed for specific kinds of applications, specific kind of load and speed regimes. So for this one, I think the answer is no. But for others that we make, the answer is yes.
Excellent, thank you. The next question references slide number 22. So I'm going to show that to the audience at this time. It's now displaying. Question is, what is the coating material in slide 22?
I will take that question. We cannot give the exact composition of the coating, but what I can say is that this coating was based on PAI binder material.
Excellent, thank you for that. And our next question is, do you have a coating solution for metallic chain conveyors?
Good question. That's a pretty broad question with a lot of unanswered parts to answer that. It depends on what you're talking about. Which parts? Like if you mean on the teeth, I'm not sure. If you're talking about the like the shafts, the gears run up.
Yeah.
The pins possibly. The pins possibly, yes. But all I can tell you is, go ahead. Go ahead, Marco.
No, please go ahead, Mike.
No, all I can say is our application engineers would love to talk to you about that. So if you want to know how to, you can go on our website, or you can contact Marco or myself afterwards. I think our contact information is going to be available, and we can definitely direct you into the right place.
Great, thanks guys. All right, next question here. In the study of composite bearings in various shaft compositions, what was more important to the reduction of wear and corrosion? Transfer film formation or shaft corrosion resistance?
Let me tell you one of the things we learned from this, in that I can't tell you, it's situation specific, but I can tell you that part of the study, when we would see this kind of a wear mechanism in the field, and we really did, our application engineers would recommend a hardened stainless steel because they thought that shaft hardness and corrosion resistance of the shaft together would improve. And we learned that shaft hardness was extremely irrelevant. We did find out, it was brand new information, the corrosion resistance of the substrate was important. And we showed that when you can form a transfer film in a stable manner, that a shaft that oxidized and wore without a stable transfer film no longer did. And so I can tell you we actually had a situation with a large construction equipment manufacturer recently where they were having this exact problem. And so what we did is, to solve the problem, we had them use this, what we call the enhanced dithering composite, together with an oxidation-resistant coating, as compared to some other bearing material and previously less corrosion-resistant material, and the problem went away. I can't tell you exactly which was a greater contributing factor, but when they did both, the problem was solved.
Great, thanks for that. All right, I just want to remind the audience, you still have the opportunity to submit your question. Just enter it in the Q&A box and hit submit, and we'll try to get to it before the close of the event. Okay, next question here. What other types of polymer coatings might be effective at reducing fretting?
Well, I'll start, Marco, if you have other, you can follow. Okay, you want to take it? Go ahead.
Yeah, I want to take it. We think that polymer-based anti-friction coatings are the best way to reduce fretting wear. This means that these coatings need to have a solid lubrication, but the family of polymer-based anti-friction coatings is quite large. As I already stated, this means we can use different polymer matrix materials to make a coating. The selection of these materials is often linked to following properties like mechanical strength, thermal stability of the coating itself. Another important question is, can I transfer the polymer into a processable coating formulation? So that needs also be answered when we formulate a new coating formulation. So yeah, it's a really broad question.
Well, I'll add to that, Marco, and I'll tell you one of the things that our GGB guys in the coating area have done recently, which I think is extremely innovative and groundbreaking, is we've got a group that's been making polymer coatings for a while, but what they've done is they've learned to develop what we call paired coatings. So two coatings that work well with each other. So it's essentially like having a system which already starts with a transfer film. And so what they do is they put one kind of coating on one side of the surface and a different kind of coating on the other. And those things are designed and tested to benefit each other. And you get orders of magnitude improvement in wear and friction by doing that as compared to using just plain old polymer surfaces which aren't designed specifically to form a transfer film. And again, contact one of our application engineers, go on our website, ask some questions, ask to talk to somebody about it, and I'm sure they'd love to do it.
Great, thanks guys. Okay, another question here in the queue. If you apply graphite, will you see that same effect of PTFE?
Yes, and let me tell you what we didn't talk about, and that is what we saw, the fluorine peaks probably weren't PTFE. And one of the things, and Marco showed a picture of that green transfer film coating, and what we know is that came from a PTFE lead. I'm not getting off the track, I'm coming back to graphite. PTFE lead, and what we know is that the PTFE gives up fluorine and combines with a lead to form a lead fluoride transfer film. And our best performing dry materials are specifically designed to form an in situ chemical reaction at the sliding interface, so that what results in a transfer film is no longer what was carved off from the bearing. So one of the things that is formed, there's a lot of literature studies on this, when you've got graphite and PTFE sliding together, is graphite fluoride. So it's not graphite, it's not PTFE, but it's graphite fluoride. And when you get in situ transfer film formation like that, that's when the transfer films are best adhered and lubricious. Because what you want is dissimilar materials sliding against each other. So instead of wanting PTFE to be carved off or graphite to be carved off and deposited on the surface, you would like for something else to form. And in the formation of graphite fluoride, and the combination of graphite and PTFE, that's exactly what's happening.
Great, thanks for that, guys. I think we're going to try to slide in one more question before we close the event. Do you need a minimum load to create a transfer film?
Marco, what do you think?
That is a really good question. As I already stated, we think that the transfer film is a response of the tribological system affected by all the different factors of a tribological system, including the load itself. At the moment, I don't think that we really need a higher load, especially when we think about when the transfer film adheres really to the substrate without any mechanical anchoring effect. For the mechanical anchoring effect, we might need to have a high load that the polymer is pushed or that the material is pushed into the roughness features. So I think it's a combination of both. We will have a mechanical adhesive interaction on the surface generating the transfer film. So maybe a minimum load is required to push the material into the roughness features, yeah.
I'll add to that, Marco, too, is that, if you have as I said, you have an in situ chemical reaction that forms the best transfer films, and so that is energy dependent. And so load and speed both will provide the energy that will help that happen.
Excellent, thanks,
okay,
guys.
Matt, that was the last one, right? Okay.
Yep, that's the last one. So thanks again for that great presentation. And thank you to all the attendees for their participation and submitted questions. Just want to remind everybody watching, you will be receiving an email from us with a link to the on-demand version of this presentation, where you can also download a PDF of the slides for today's session. Thank you again for taking the time to attend this webinar event. Take care, and we'll talk with you soon.